shop. I've talked about myself a little bit on the autobiography, so I figured on this video I'd talk about a little bit of things I've been doing. I'd start with the small projects, and then we'll move to the large projects. So I do a bit of machining for my regular job, and when I'm at home I like to work on my own projects. So I guess we'll start with my chip bag clip that I've got here. This clip is machined out of aluminum, and I did it on a Kuma, just a 3-axis mill. It actually took, let's see, 5 different setups to do on the 3-axis mill. So you can see that one side has kind of got a dull finish, while the other side has got the shiny finish there. That's actually because I set up a production run, and some of them were sandblasted at the end of it and some of them weren't. And I figured this chip clip would be a good show of what I've done. So the first thing I wanted to point out is that I designed this thing around this spring that's on the inside here. I had a bunch of these. I had gotten them for free from a guy who was just cleaning out his shop, and I didn't originally know what I was going to do with those springs when I got them, but I've got a box full of them, and I thought that this would be a good application for it. I mean, it looks super beefy, but it's actually not too bad for a clip spring. So it worked out pretty well. So the way this started out is that my wife was complaining that our plastic chip bag clips kept breaking, and we'd be going through them fairly regularly. We've got a couple of young kids, and they're really hard on those things, and if they get a hold of them, then we'll find bits and pieces of clips everywhere in the spring here and there, and it just wasn't a good situation. We didn't want them swallowing the springs or any of the parts or anything like that. So I thought it would be a fun project while I was in machining school to make one. And at the time when I started designing this, I had didn't have a whole lot of CNC machine knowledge. So I designed it from a very simple design. And I can actually show you the original design here. I'll show it to you real quick. Okay, so this is the original design, and I'm just using a drill bit that's the right size for the pin to go through this thing, just to kind of put it together and show you. I had printed this out on a 3D printer before I ever machined it. So basically it consists of the 4 parts. The spring, I'll pull this apart for you. So you got the 2 sides. I'll set these there. The spring, and then the rod that'll go through it, which in this case is just the drill bit there. So these sides here, I thought this was a little heavy to be used as a chip bag clip, and it's not too bad, but it is kind of bulky and whatnot. So I thought that that I could do better and put holes in it and lighten it up that way. And that's when I had went through a whole bunch of different ideas, and then I finally came up with this design right here. I put these in there so that would hold the spring in for easy installation and whatnot. And I decided on the other clip, if you can kind of see in there, that I've still incorporated that into the other design. It's just a little notch right in there where the spring fits in. And then, and that's on both sides there. So, and then I decided that it would be convenient to add little magnets and maybe a hole on the other side to be able to hang it up on something if you wanted to hang it up. And that would kind of help out with the whole bulky, heavy feel to it, so that you just hang it up instead of it sitting on a shelf or whatever and flopping over. So these magnets are neodymium magnets, and they're pressed in. It's a press fit that I'd machined out there. And originally I was thinking I'd have to glue them, but then I thought if I made it just the right fit, that it would fit well. Neodymium magnets are a hard material and they're kind of brittle, or it's kind of brittle. So I figured if it was going to be a tight fit, that we would need to, that it might possibly end up breaking the magnets when I was pressing it in. So I figured, to be on the safe side, that I would leave it pretty close fit, and then if I needed to, I'd glue it. So there's probably about a half a thou interference there. So the aluminum does put a little bit of a squeeze on the magnet, but I think it fits actually really well, and we haven't had these come out or anything. Each one of these magnets were rated with a 7.5 pound lifting strength, and which kind of seems overkill, but actually it turned out really well. They stick decently, and it'll hold up things, and you could probably even put a book on your fridge with it if you wanted to. But it's not hard to pull off the fridge, and I think that way it worked out pretty well. The next thing that I had considered about when I designed this thing was how well it was going to grab. This original design here didn't grab very well. If you look at those angles there, if you threw something in there, it would have a funky angle while it was grabbing it, and could have the potential of it slipping out once it squoze down. So I decided that I would put a few teeth on it, and then I'd change that angle just slightly, that the two sides of the clips engage. And I threw these teeth on here. And that was a little bit of a challenge when I threw those teeth on there. And let me see if I can get a better shot of these teeth that are on there. So those teeth were a little bit of a challenge to machine, because I didn't want to set it up and have to machine each one of the teeth out individually. So I actually custom designed a cutter for it. And that cutter, well, I can show it to you. I'll show it to you real quick. Okay, so this is the cutter. And it is machined at the exact angle that this face would be while it was sitting at a 90-degree angle on the machine. So mounted up there, this would come along that face and come across it, and machine those teeth out, and it could do it in just one pass. This is a tool steel. I actually took an end mill that had been ruined, and I just took the shank of the end mill and machined this out of it using a carbide cutter to machine this. So this is high-speed steel, and I machined it so that it would fit, or I'd machined it on a lathe at first, and then I put it in an indexing machine and had machined those flutes into it. And it actually turned out really well for aluminum. I haven't had any problems with it. And I had taken a honing stone and kind of polished up those flutes a little bit so that it had a nice sharp edge to each one of those teeth. And so that worked out pretty well. So that was how I made those teeth in there. Let's see, what else can I say about it? I don't think there's really too much more to say. So this is the chip bag clip. And this was just one of my ideas. The next idea I'll show you. Okay, so this is the next project that I'd come up with. This was also done in machining school. So how this came about was, well, first let me tell you a little bit about what it is. So this is a planetary gear system, and it's all made out of aluminum. And those teeth come around as you turn this, and it's a 3-to-1 ratio. So for one revolution of this shaft there, the shaft in the back will turn, so for every 3 revolutions that this shaft makes, the one in the back will turn once, which was kind of a fun project. My instructors in machining school were looking for a fun project that some of the students could do that would actually produce something. So parts and pieces that would eventually come together to make something. And a lot of the machining projects and things that they have in machining school, at least the one that I went to, had simple little things that would just test your ability to machine certain things, and then that would be it. You'd toss it or whatever. If you were proud of the work that you'd done, you put it up on a shelf and it'd just sit there. But it would have no other use besides that. And so I thought it'd be kind of fun to make a project that could actually be useful for something. As for me. But I had figured out, so all of this just kind of snaps together, and then each of these gears can come out, and it's just a loose little clearance fit on each one of these pegs there. So each one of these can come apart, and so you've got several pieces that make up the whole part there. So anyway, in order to, because the school that I was going to didn't have any involute gear cutters or anything like that, nothing fancy. We just had CNC machines, and so I thought the best way to do this would be to use the smallest end mill that we had and just mill out each one of these teeth. And since it was all CNC work, it's not really that big of a deal to do it that way. So this is an 1/8 inch end mill that made all of these grooves there, or the teeth, and it was a bit of a chore because I had no idea what I was doing when I first started this project. It was a little bit tricky at first to figure out how many teeth each one of these were going to need in order for everything to line up. And I had originally come up with, I can't remember what number off the top of my head, but I just kind of come up with some numbers for the gears, and I threw it all together, and then I tried it on a solids model in SolidWorks, and it didn't end up working out. When I put it all together, none of the teeth would line up or anything like that. And then I realized that when you're doing a planetary gear system, the ratio of each of the gears is a huge deal, and I didn't really think about it at the time. So what I figured out is that everything in here has to be divisible by each other. So these teeth, and I don't remember off the top of my head, so maybe we'll just count them. So each of these are 12 teeth. And then I believe this gear is a 36 tooth outside gear, which of course is divisible by 12. If you think about it, in order for this gear to go around, all 12 of these teeth have to line up at some point. And so in order for that to work properly, these, to make it a third of the way around, they have to have the proper amount of teeth to line up again when they've gone a third of the way around this circle. So 12 teeth and 36 teeth. And so that works out really well. So that's how I figured that one out. Took a little bit of trial and error, but shouldn't be that difficult to figure out. And so all of it just kind of snaps together, and these are little snug fit pins there, and they just come together, and then the whole thing stays together. So that was one of my projects that I've done, and that was kind of fun. All right, and then the next one, this is actually straight out of a book that I had bought called Mechanical Movements. I think it was 500 and something mechanical movements. And I bought it off of Amazon just to kind of give me an idea of some fun projects and things that I could do while I was in school. And it was another. So this particular project is actually I designed this and built it for practice in a Skills USA machining competition where you had to it was CNC work, and you would come up, or they would give you a design, and you would have to make blueprints for it, a solids model of it, and then do the cam work for it, and then run the cam tool pathing in the CNC machine and make those products. And I believe halfway through the Skills USA competition, they would throw kind of a wrench in the works, and they would say that there's been a change to the order, and they would either add in a piece, or they wouldn't take out a piece, but they would add in a piece, or they would change something major on one of the designs of one of the pieces. And the whole project is kind of testing your manufacturing abilities to go from just a drawing to a finished product. And in the past, teams would have 8 to 10 hours, I believe, and they had shortened it for us. I believe we had to do the project in 6 hours, if I'm not mistaken. I can't remember now. But so this is one of the things that I designed for practice because it had a lot of parts to it, and each one presented its own challenge for how you would mount it, and it's also a test of accuracy and precision when you're taking a look at the final outcome. Because if any of these things were in the wrong location, this would not rotate around very well. As you can see, each one of these pegs here have to line up perfectly with their slot all the way through the range of travel in order for this thing to work, or else it would just bind up. So it's actually a really good test of your machining ability and your precision, and how well you can get parts that you've made to line up correctly. And this is all done out of aluminum. And then there were a couple of brass pieces that I threw in there for little brass bushings that would go on each of the things. And these are in 2 pieces. So let's see if I can get one of these out. I think I peened one of them in. But they would provide a little bit of lubrication. In my original design, I had a center drilled hole at the top of this just so you could oil it if you wanted to. But my machining instructor decided that would be too time consuming because it would be a whole nother setup to put that on there. So we left that one off. So this is just a little piece with pegs in it. And then you have those little brass bushings in there. And then if you look in it, it's actually two separate brass bushings that press into each side there. And then you've got that little groove in the middle, in between the two, that would be able to hold oil. So I just thought that would be a neat little way of doing it. So that groove there would hold oil, and you could oil it once and it'll stay oiled for quite some time before it needs to be re-oiled. So anyway, so there's that project there. So this was just for practice for Skills USA. And I believe it's been a little over a year since I've graduated from machining school, and they are actually using this design for some of the school projects as well. So that kind of worked out well that way too. So I think that's actually the interesting thing about this thing is the gear ratio here is a 2-to-1 ratio. So every time I turn this, and we'll take a look at that little hole over here, and we'll watch it as I turn this around. So I'm going to start at the bottom, and we'll go once around, and so that's the other side of that hole, and then twice around, and then that's the hole. So that made 1 revolution when I did 2 revolutions on that side. And the reason, the way that works is the inscribed circle of this machined part is half of the size of this machined part. So that's how it makes the 2-to-1 ratio there. So there's another project. Now we'll move on to some of the bigger projects that I'm working on. The main project that I'm working on, and we'll move over to it in just a second, is a foundry furnace. But let's go take a look at the foundry that I'm working. Okay, you're gonna have to bear with me while I show you this thing, because I'm gonna be holding the camera the whole time, and it might be a little bit shaky. But let's flip the camera around, and I'll show you what we're doing here. Okay, so let's start at the tank. Let's step back a little bit so you can see the whole picture there. Okay, so that's the oil storage tank, and then you've got the filters right below it, and I'll tell you about the filters in a minute. And there's the furnace that I'm putting together, and currently I'm about to put insulation in that insulation jacket around there, and I'll show you that in a minute too. And that's what all that stuff sitting on top of there is for, and this huge mess. Okay, so this is the tank, and I've got, all right here, this is a clear line that's kind of closer to the bottom of the tank that'll tell you when the oil's getting low inside the tank, because you'll be able to see it through that clear line there. And then you come down here to this system, and I'll talk about the bottle. So this right here is the lowest point of the tank, and so I figured that would be a really good way to have a gravity operated water separator. And so all of the water that's inside the tank there will flow down and end up in the bottom of this jar, which of course is just a mason jar, as you can see. And you just unscrew the mason jar after you flip this valve off, and you can dump out the water out of that oil from the glass jar. So I put a pipe inside of this jar that goes down to about the top of that oil level, so that when you flip the valve off, you're not going to overflow the bottle. Once you unscrew the bottle, what's in this pipe is going to drain into the bottle, but there's enough room at the top of the bottle for that oil to flow into the bottle without overflowing it. So that was the idea there. All right, so next we've got our main fuel valve, and this valve drains down into a tank, and that's all gravity fed too. And this tank is I don't know if you can see that very well. Okay, so that's a 10 thou filter, and I can show you pictures of that in just a minute here too. So this 10 thou filter is going to filter the oil, and most of the heavy particles and stuff will end up in the bottom, which you can change out through unscrewing that. And so this also kind of works as a low point as well. So if there is any additional water in the oil, it'll flow down to the bottom of this as well. And then the oil's got to climb up and over and then into the, see if I can throw. So there's a 50 micron filter in there, which I've also put in there. And both of these filters are stainless steel. So they can be cleaned out easily, and I can throw them back in there. So then same thing with this one, there's another low point here, and you can take out the filter from there. I'm sure that's going to be pretty messy when the time comes to change that out, but you know, such is life. Okay, so the oil will flow up to the top of this and then over through this tube and then into the Bosch car filter that I've got here. And this car filter is supposed to filter it down to about 7 microns or so. I may be wrong on that number, but that's what I've gathered from doing my research. And then from there, it's going through this silicone tube, which is extremely flexible, so I had to wrap some wire around it to keep it from kinking right there. And this is going to go into this coil. And this coil is going to sit right on top of the furnace, right over the exhaust vent. And some of you who have used furnaces before know how hot that exhaust gas gets, or at least have an idea. So in order to keep the oil from getting too hot going through that coil, I have devised a little temperature controller, and it's a microcontroller that will rotate that out of the way. And this will be on a little rotating peg that'll just swing out of the way. And then when it cools down, the temperature controller is going to activate, and it'll swing right back over the exhaust. And it'll keep doing that back and forth until or to maintain the temperature of the oil. And I'm trying to get the temperature to about 180 degrees. And from there, it's going to flow into a centrifuge, which I haven't really finished putting together yet. And that's the centrifuge. It's going to separate all the heavy particles out of the oil, and it'll be the last filtration step before it goes into the oil management block. So it'll go from that to a collection tank, and the collection tank is right down here, and this is actually used to be an old helium tank for filling up balloons. I figured this would be the perfect use for it. So it'll drop into this tank, and then a pump is going to pump it out of this tank to the oil control block. And this oil control block I will go into more detail on sometime later. But this was my own invention here, and there's a little ball valve on the inside of there that maintains pressure, and by tightening the screw on the top there, it'll put more spring pressure on that ball valve and it'll increase the pressure. And then I've got a little pressure indicator here that'll tell you what the pressure level is at. So there will be a continuous cycle going from the pump to this back to the collection tank over there, and that collection tank is going to be the tank that's going to have the temperature monitored on it in order to swing this out of the way. Okay, so I'm going to regulate the pressure to 15 psi, which is what the manufacturer recommended for the atomizer nozzle that I've got at the end of this. And so there's the tube that comes out the bottom there and into the airflow duct, for lack of a better word. And I'll pull this out of here. And it's a fairly tight fit there, and that's refractory that it's pushed into. So I'll pull this whole thing out and we'll take a look at that. Okay, so it's going to go through here, through this pipe, and then on the side of this, there is a bleed air system there. As the air flows through this pipe, it's going to be restricted right in this area, which will drop the pressure, but it'll speed up the air going around it, which will pull air through this hole right there. And that hole gets its bleed air from that pipe right there. And I'll show you that a little more in detail in a minute too. Okay, so if you look down this tube right there, you've got the atomizer at the end of that oil tube, which kind of skirts around that restriction there. And this is supposed to, the bleed air that comes out of this is supposed to do a final heat on that, on the pipe and oil before it atomizes and goes out for combustion. So that's the idea there. This screw sitting out the back of this thing is a throttle valve, and that's going to, after the oil has been pressurized to 15 psi, that's going to control how much of that pressurized oil will reach that nozzle. So that's what that's for. All right, so I've got a foot pedal down here, and that was an idea that I got from the Artful Bodger. You'll have to, I'll show a link there to that as well. So I'll push down the pedal and it lifts up the lid. We'll move this out of the way. And this. We'll swing that to the side. And then on the inside there, the airflow comes from that duct there. Let's see if I can bring the camera down to show you a little better. So it comes through that duct right there, and it swirls inside the furnace. And the furnace height is calculated so that I can get as much combustion inside the furnace as possible before the flame is ejected out the top through that hole. And then as this swirling effect happens, there's another hole, which is my bleed air hole, which is right there, which goes back to that side duct there, which will be injected for preheating the oil. So that's the idea there. And then with this lid right here and the foot pedal, as soon as I let go of the foot pedal, the lid should drop down, and it'll just hold itself on the side there so it doesn't swing around freely and you know, a hot lid could end up burning you while you're working on the crucible or whatever in there. So here's my little block, my riser block that sits right down in there. And then I've got my crucible, which will sit on top of that. And I don't know what the capacity of that crucible is, but I have used the refractory lining of the furnace to also make that crucible. And the refractory is supposed to be rated at 3,000 degrees Fahrenheit, or about 1,700 degrees Celsius. And that's that should be hot enough to do cast iron fairly easily. All of these ideas I had gotten mainly from that Artful Bodger book. So that is the furnace, basically. Eventually, right where this stuff is, I'm going to have a control panel with switches and things to turn on the various systems for the furnace, and I'm probably going to take that pressure indicator and bring it up to the control panel so that you can monitor it from the control panel. Let's see. Oh, the blower that I've got here is just a Harbor Freight blower. I took out some of the vent pieces from it so that it'll not restrict the airflow as much as possible. I realize that it's going from this huge area down to the smaller pipe, which is about a 2-inch pipe on the inside. But I'd like to keep as much restriction out of the system as possible, just to help out. So yeah, that's pretty much my furnace, and I think I'm going to cut this video about here so that it's not ridiculously long, even though it already is. And that is my first video for YouTube. So I've got a huge mess here to clean up, but I've been working, so it is what it is. All right, so long.